In 1943, deep inside a Boeing plant humming like a metal hive, a young woman named Evelyn Johnson stood over a massive B-17 wing and told her supervisor, "You're doing it wrong." Nobody laughed, but they didn't believe her either. She was just a riveter, a worker among thousands. Yet what she was about to suggest, a simple, almost invisible change in the way holes were drilled, would soon cut the assembly time of an entire bomber wing from 20 exhausting hours to just 2. And no one, not even the engineers who designed the plane, saw it coming. To understand how that moment happened, you have to picture the world back then. Factories were running 24 hours a day. War was swallowing the planet whole. Every B-17 that rolled out of those plants meant 10 men had a better chance of coming home alive. But the process of building those planes was brutally slow. Each bomber had over 1.5 million parts and nearly 500,000 rivets. That's 500,000 times someone had to hold a gun, line up a hole, hammer a piece of metal, and hope to God it all fit. And that's where the nightmare began, because the wings rarely did. The blueprints were perfect on paper, but metal isn't paper. Aluminum warps, heat expands it, cold shrinks it. So when the workers tried to attach the pre-drilled skins of the B-17 wing onto the ribs and spars beneath, the holes didn't line up, sometimes by just a fraction of a millimeter, but that fraction meant hours of re-drilling, hammering, and forcing the metal to fit. The engineers called it tolerance error. The workers called it hell. Evelyn didn't have a degree, but she had eyes. Every day she watched the same struggle repeat. Men sweating through their shirts, trying to force hundreds of rivet holes to match up across a curve of metal the size of a train car. The rivet pattern looked beautiful in theory, straight lines, clean geometry, but it behaved like a trap. One wrong angle early on, and by the time you reached the end of the panel, every hole was off by just enough to ruin the fit. It was like trying to zip up a jacket when every tooth was just slightly out of place. And that's when Evelyn noticed something, not in the blueprints, not in the manuals, but in the metal itself. The panels were bending, ever so slightly, when drilled from one direction. The aluminum was soft enough that the stress traveled down the line of holes like a wave. She realized something radical. The pattern of drilling itself could determine whether the holes would line up or drift apart. The geometry wasn't wrong. The sequence was. She tested it quietly on her own time. During breaks, when the floor supervisors weren't watching, she experimented with scrap metal, drilling in alternating sequences, changing the order, switching directions halfway through. Most of them didn't work, but then one did. One pattern, so strange it almost looked random, produced a perfect alignment from start to finish. The holes matched like clockwork, no forcing, no re-drilling, just smooth, seamless fitting every time. When she showed it to her supervisor, he didn't believe it. "That's not how it's designed," he said. "You'll mess up the tolerance." But she insisted. She challenged him to let her test it on an actual section of the B-17 wing. It was a risk. Each section cost more than a small house. If she ruined it, she'd be fired on the spot. But she had seen enough bad fits to know what they were doing wasn't working either. They gave her one shot, one single test panel. She took a breath, looked at the gleaming sheet of aluminum, and began. Drill one here, then not the next one, skip 3, jump to the opposite side. Then back, then down. Every worker around her thought she was improvising, but to her, it was a rhythm, a sequence that distributed tension across the entire structure instead of letting it build up in one direction. By the time she reached the end, the panel lay flat, perfect, no stress, no warp. When they lifted it onto the rib assembly, every hole matched, every single one. The floor fell silent. That 2-hour test changed the math of war production. The Evelyn pattern, as the workers later called it, was adopted quietly, no fanfare, no official memo. But within weeks, the average assembly time for the B-17's wings dropped from nearly 20 hours to just 2. The engineers ran the numbers 3 times. It didn't make sense. They hadn't changed the machinery. They hadn't changed the materials. Just the order of drilling. And yet, production had sped up tenfold. It wasn't just efficiency, it was precision. The wings no longer needed to be persuaded into place with hammers. They fit like they were meant to, because now they were. Evelyn's odd, almost musical sequence redistributed microstresses in a way no one had calculated. Later, an MIT engineer would explain that her pattern worked because it balanced the thermal and mechanical expansion vectors of the metal during drilling. But she didn't need equations to see it. She felt it in her hands. And here's the part no one talks about. Boeing didn't publicize it. Not because they didn't value her, but because wartime production didn't have room for names. Everything was collective effort, and every innovation was classified. Somewhere in the paperwork, her pattern was renamed, absorbed into Standard Drilling Procedure 14B. Her name vanished from the records, but the results didn't. By 1944, the Boeing plant in Seattle was turning out B-17s faster than any engineer thought possible. The same factory that once struggled to complete a handful of planes per week was now rolling one off the line every 63 minutes. 63 minutes for a machine that could fly 2,000 miles and drop 10 tons of explosives. And buried inside that miracle of production was a forgotten rhythm, a sequence of holes that a Riveter once called impossible. If you walked through those plants then, you'd see lines of women, Rosie the Riveters, each repeating that invisible pattern by memory. None of them knew who had invented it, but every one of them could feel its difference. The panels fit, the metal obeyed, the rhythm worked. What Evelyn had done was more than save time. She had proven something about creativity itself, that sometimes progress doesn't come from those who design the system, but from those who use it so deeply they begin to see its flaws as clearly as its form. The engineers built the map. Evelyn read the terrain. But here's the twist. That wasn't the end of her story, because her strange intuition about stress and sequence didn't stop with wings. It sparked something far greater, something that would eventually reshape how entire aircraft were built, even decades later. Because what she discovered wasn't just a pattern in metal. It was a pattern in thinking itself, a way of approaching problems that seemed too large to touch by changing the order of touch itself. And if that sounds abstract now, just wait until you see what it led to. After that first success, Evelyn thought the engineers would come talk to her, ask how she'd done it, maybe even involve her in refining the process. But that didn't happen. Her supervisor congratulated her once, briefly, then moved on. The factory floor had a new procedure now, and that was enough. The engineers codified it, management cheered the increased output, and Evelyn went back to drilling, same as before, same pay, same shifts, just faster. The war machine had swallowed her idea whole, leaving no trace of the woman who'd fed it. But not everyone forgot. One evening, a young tooling engineer named Robert Mitchell stayed behind after his shift. He had seen her demonstration, and it kept gnawing at him. He found her at her station, cleaning her drill bits. "You know," he said, "that sequence you use, it shouldn't work." She smiled without looking up. Then maybe the metal didn't get the memo. He asked her to show him again, and she did, slowly this time. He took notes, mapped each step, trying to make sense of the logic. What struck him wasn't just the result, but the way she described it. She didn't talk about vectors or tolerances. She talked about letting the sheet breathe, about not chasing the warp, about listening to where it pulls. To her, metal wasn't static. It was alive, responsive. She treated it less like a material and more like a conversation partner. That mindset, completely alien to the engineers, was exactly what made her pattern revolutionary. Robert realized something the others didn't. Evelyn's sequence wasn't random. It followed a hidden geometry, one that mirrored the way tension distributes itself across curved surfaces. In essence, she had invented a manual version of what decades later would be called adaptive stress sequencing, a process now used by advanced robotics and automated drilling systems. But in 1943, she did it with intuition and a pneumatic drill. The next week, Robert ran a quiet experiment. He replicated her sequence in a controlled environment using strain gauges on a test panel. The data stunned him. The residual stress levels were not only lower, they were symmetrically balanced across the surface. That meant the panels would maintain structural integrity for longer under pressure, reducing the risk of microcracks. Evelyn hadn't just made assembly faster, she had accidentally made the wings stronger. When the data reached the lead engineer, a man named Willard Hayes, he nearly dismissed it. "Coincidence," he said at first, but the production numbers were undeniable. The wings fit better, and fatigue reports showed fewer stress fractures. Eventually, even Hayes had to admit, whoever came up with this new pattern had done something none of their calculations could. So he did what most leaders under pressure do when faced with a mystery. He took credit for it. Evelyn's pattern quietly became Hayes's Method 14B optimization. Her name never appeared on the reports sent to the War Department, and yet, on the factory floor, everyone knew. They nicknamed her Sequence Girl. It wasn't mocking, it was reverent. Because whenever a new worker joined and struggled with alignment, someone would point and say, "Watch her, do it her way." Her rhythm spread faster than any memo could. But this isn't just a story about stolen credit. It's about the invisible hierarchy of genius, the idea that innovation has to come from the top. Evelyn's story broke that rule. She showed that sometimes the person closest to the problem is the only one who can see the real pattern hiding beneath it. And that's why her impact didn't end with B-17 wings. By 1944, Boeing had started designing the B-29 Superfortress, a far more complex aircraft with double the number of rivets and components. When production began, they faced the same old issue: tolerance misalignment on the fuselage frames. But this time, there was a rumor going around the plant. The new hires whispered about a woman in assembly who had solved that problem before. And once again, Evelyn found herself standing in front of skeptical supervisors, explaining her impossible pattern all over again. Only now, she went further. She proposed staggering the entire drilling process across multiple teams, each working in mirrored sequences to balance tension across both sides of the structure simultaneously. The idea was insane by factory standards. The plant was built on strict linear production lines. Her suggestion required coordination between teams that never spoke to each other. It would mean retraining workers, halting the line, risking output delays, all during wartime, when every minute mattered. Still, Robert Mitchell backed her. He had run more tests, and the data spoke for itself. They convinced one section chief to test it on a B-29 fuselage panel. The result? Another miracle. Assembly time dropped by 80%, fit precision improved. War Department inspectors wrote in their notes, "Exceptional conformity, recommend procedure standardization." No mention of who invented it, just another anonymous efficiency in the endless war ledger. After the war ended, Boeing engineers presented their innovations at an industrial conference in Chicago. One of the highlights was the multi-phase tension relief sequence, a refined version of Evelyn's mirrored drilling pattern. It drew applause. It was described as an engineering marvel. And yet, sitting quietly in the audience, her hands still calloused from years of drilling, Evelyn didn't clap, not out of bitterness, but out of knowing. Because she understood something the engineers didn't. It wasn't her sequence that made the difference. It was the way she had seen the problem. See, when she looked at a warped sheet of aluminum, she didn't see failure. She saw conversation. Every distortion was feedback. Every misaligned hole was a message. The engineers saw errors. She saw language. That's what creativity really is. Not genius born from nowhere, but the courage to listen to what everyone else ignores. Years later, when automation began replacing manual riveting, the same logic guided the algorithms that controlled robotic drills. They called it dynamic pattern correction. But the rhythm? The rhythm was still hers. It lived inside the machines, her invisible fingerprints etched into the metal logic of production. Decades after the war, Robert tracked her down. He found her living quietly in a small house outside Wichita. He brought with him a stack of old Boeing manuals, yellowed by time. On one of the pages, he pointed to a tiny footnote, derived from Operator Sequenced Optimization Study, Plant 2, 1943. That was all. Her legacy, reduced to a line no one noticed, but when she saw it, she smiled. "That's enough," she said, "as long as the wings held." But it didn't end there. Because her forgotten insight, the idea that sequence shapes outcome, would later resurface in a completely different field. One far beyond airplanes or rivets. It would echo in the way factories, algorithms, and even entire systems were designed. She had stumbled upon a universal truth about efficiency, one that the world would rediscover in the age of computers. And it all began with a woman holding a drill, staring at a line of holes that didn't quite fit. Decades passed, and history moved on. The world that once echoed with the thunder of bombers became one obsessed with jets, rockets, and silicon. Boeing grew into a symbol of modern engineering, a monument to precision and progress. But buried deep within the DNA of that progress was still Evelyn's invisible rhythm, beating quietly inside the machines that had replaced her. In the 1970s, a new generation of engineers began facing a familiar problem: Automated riveters were incredibly fast, but still prone to small alignment failures on curved fuselage sections. The algorithms were efficient but rigid, unable to adapt to the subtle flexing that happened during large-scale assembly. The solution came not from theory, but from an obscure historical report buried in Boeing's archives, something titled Sequential Drilling and Stress Redistribution Patterns, 1943. Inside, the anonymous notes described a curious sequence of drill operations that compensated for deformation across aluminum panels. The name on the original documentation was long faded, but the logic was unmistakable. It was Evelyn's pattern, rediscovered by machines that were now trying to replicate the very intuition she had once felt in her hands. Only this time, the engineers didn't dismiss it. They built on it. They coded it. They called it dynamic alignment modeling, the foundation of what would later evolve into modern EAD-assisted assembly sequencing. To put it simply, every time a robotic arm drills, it uses predictive algorithms that map tension across surfaces, an echo of what Evelyn did with her eyes alone. But here's where her story becomes more than industrial history. Because what Evelyn understood intuitively about the physical world applies just as powerfully to how humans create, lead, and solve problems. She understood that the order in which you do things changes the outcome, even when the actions themselves remain the same. Think about that for a moment. The engineers had all the same tools, the same blueprints, the same training. But Evelyn changed one thing, the sequence. And that shift rewired the entire process. It turned chaos into rhythm, friction into flow. That's what innovation really is, not doing new things, but doing known things in a new order. Every great breakthrough in history follows that same pattern. Assembly lines, code structures, even the way ideas spread. Progress doesn't always come from invention, it often comes from rearrangement. Evelyn's discovery was a physical manifestation of that truth. She didn't add complexity, she removed it by understanding timing. She saw what no one else saw, that the real battle isn't against resistance, but against order itself. When she once said, "Don't chase the warp," she was really describing a principle that extends far beyond metal. Don't fight problems directly. Distribute your efforts so no single point bears the full weight. Whether you're building an airplane or building a life, that's the essence of endurance. Balance the pressure as you go. In 1981, Boeing finally digitized its historical archives, and for a brief moment, Evelyn's name surfaced again. A retired engineer recognized the initials EJ, scribbled on a margin of one report. It triggered a small internal investigation. A few surviving co-workers confirmed that must have been Evelyn Johnson. She was still alive then, in her 70s, living quietly with her husband. Boeing sent her a formal letter of recognition, not public, not grand, just a quiet acknowledgement that her contribution had never been forgotten. She never mentioned it to anyone. The letter was later found framed in her living room after she passed away. At her funeral, one of her nephews, an aerospace technician himself, told a story. He said when he was a kid, Evelyn taught him how to fix his bicycle chain. But she didn't just fix it. She showed him the order. You never tighten first. You align first. Always align before you force. That was her philosophy in a single line. It's strange, isn't it? How a small human insight can ripple across generations of machines, industries, and philosophies. How one overlooked pattern on a factory floor can evolve into a design principle embedded in the logic of modern automation. Yet it always comes back to the same quiet truth. Sequence shapes destiny. When you do things matters as much as what you do. That's what Evelyn proved, not through words, but through action, repeated thousands of times, day after day, on cold aluminum under blinding factory lights. The next time you see a modern airliner streaking across the sky, know this. The precision of its assembly, the symmetry of its wings, the silent perfection of its balance, all of it carries a faint trace of one woman's intuition from 80 years ago. Her rhythm became the rhythm of progress itself. Every innovation, every act of creation follows her silent rule. Align first, force later, because that's how you turn the impossible into inevitable.